Are we ready?
We're done the camera. Okay.
Howdy, we are nPhase. I'm Ryan Holt, project manager.
William Caster, software engineer. Cole Hooten, software engineer. Caleb Odom, lead hardware engineer.
William Connor, hardware and systems integration engineer.
First off, we'd like to give a special thanks to our sponsor, Osmer Watanabe of Watanabe Tecnologia Aplicada, and our technical advisor, Dr. John Walsart. Brief summary of what we're going to go over today. We've got our introduction, which includes our problem statement and concept of operation. Project overview, which includes our functional requirements, conceptual block diagram, performance specifications, and our functional block diagram. Technical presentation, which includes our schematic, board layout, enclosures, and software flowcharts. Our demonstration, and then finally a summary section of our project so far, including our overall status, major tasks completed, deliverables timeline, Gantt chart, and our financial status, and then we'll end on the Q&A. So to begin, our problem statement, agriculture is a necessity of modern society, but many of the methods are stuck in the past. Monitoring livestock is time-consuming and inefficient, and there is a need for a wireless sensor tag for monitoring livestock. nPhase has been tasked with the design, development, and delivery of an embedded sensor suite and wireless communication system. Together, these are called the Internet of Cows, or IOC for short. IOC will be used to provide accurate and up-to-date information about the temperature and cycles and movements of livestock. A little background, studies have shown that about 15% of cattle are determined to be in heat are falsely identified due to inaccurate identification methods. To confirm the status of being in heat, many ranchers have to isolate the cow with another sexually active cow, or some sort of heat detecting animal like a donkey or something like that. For our concept operation, we will be creating a fully functional prototype of a mobile wireless monitoring system. To test the IOC system, a temperature-controlled environment and cattle analog will be used to simulate the conditions that the IOC prototype will be used in. Once the prototype is finished and ready to be delivered, it will be installed by WTA at one of their cattle ranches. An on-site server will collect data from the prototype, and the data will be then compiled into a report and displayed on the web page. The prototype will be used as the basis for Watanabe Tecnologia Aplicada to mass produce it as a product.
So now we have our functional requirements. We have 6 of them. First is a small form factor. So the IOC prototype must be able to fit within a small enclosure. Next we have power consumption. The IOC prototype must be able to operate for long periods of time without swapping the power sources. Next we have real-time update requirement. So our prototype must be able to provide up-to-date information to a server. Next we have accurate temperature measurements. So the IOC prototype must be able to accurately measure the ambient temperature around the cow and the actual temperature of the cow itself. Next we have close-range wireless communication, and all the information from the prototype must be able to communicate to a nearby antenna. And then last we have the accessible data requirement, so all this data must be accessible to the customer. So here we have our IOC prototype, a conceptual block diagram. That's our MSP430 FR2311 microcontroller. It will be supplied with 3.3 volts. Our first sensor is an accelerometer communicating via the I2C protocol. Our 2 temperature sensors are the ambient temperature and the internal cow temperature. The ambient temperature will also be using I2C, whereas our internal count temperature is just an RTD with an analog signal. All the information is going to be compiled into a packet and sent via the UART protocol to an RF module. This is the CC1310. All the information will be sent to another CC1310, which will be then connected to our laptop that will then be displaying a web page. So all the functional requirements have, of course, a performance specification. And the first one of those is the small form factor. Our enclosure must be able to fit within a 2x2 by 0.5 inch enclosure. Next we have our power consumption. We must be able to operate at least 1 month without swapping the power supplies. Next we have real-time updates. The prototype must be able to communicate and provide updates once every 3 hours to the server. Next we have accurate temperature measurements, and those measurements of the cow and temperature of the cow will have to be within 0.15 degrees Celsius. We have our close range wireless communication. All the information must be within 50 meters of the cow. And lastly, all of the information will be displayed on a web page to the customer.
So now we have our functional block diagram. This is just an overview of everything we have going on. We're going to zoom in so you get a little bit more detail and be able to read a little better. This first section includes our battery And our voltage regulator is a 3.7 volt battery, which is going to be using the voltage regulator to go down to 3.3 volts, as well as it has another volt output of 3.0 volts, which will be used to power our load switch, which is the load switch is so we can turn off the weak zone bridge, which is used to get accurate temperature readings from our analog temperature sensor. We want to be able to turn that off and on because the weak zone bridge takes up a lot of power, and we want to be able to reach the 1 month. And we're getting those readings by connecting the weak zone, measuring ADCs across the weak zone bridge using 2 ADC pins on our MSP430. Next, we have our CC1310, as well as its connection to the MSP430. Over there, we have our JTAG, and we're actually, CC1310 is another microcontroller, so we're actually doing daisy chaining, so we can program both the microcontroller, the MSP430, as well as the CC1310. We're doing so by having the TCK and TMS lines tied to both of them, and then we have the TDI line of the JTAG header going to MSP430, and the TDO line of the MSP430 going to the TDI line of the CC1310, and then that TDO line going to the TDO of the JTAG. And as you can see up top here, these 2 pins for TDO and TDI on the MSP430 share functionality with our UART protocol, and we can actually do both of those on the same pin by using the test pin on the top of the JTAG header. If we pull it high, we can program it using JTAG. If we pull it low, those pins will then be used for the UART protocol. And then down here in the 1310, we have it goes to a balance, which is used for impedance matching. Instead, we can either apply circuitry, go to the antenna by doing a bunch of capacitors or inductors, but this does the exact same functionality, but conserves space and does the exact same thing. And then we have it go to 100 picofarad capacitor.
I don't know what you mean by we have. How about a whip?
And then from that 100 picofarad capacitor is a 50 ohm trace to our sticker antenna, which will be connected to our enclosure. We also have a 24 megahertz crystal that's going to be connected to our CC1310. Next, we have a look at our I2C sensors. They're sharing the exact same 2 I2C lines, and they'll both be pulled up with 1 kilo ohm resistors. The only other thing to point out here is we have the chip select, which needs to be pulled low to be using the accelerometer sensor, and then we also to use it in I2C mode. Otherwise, if we pulled it high, if we pulled it high, then it'd be done in SPI protocol. Then we have an accelerometer interrupt, so we can start receiving the data, which is connected to a GPI open on our MSP430. Next, we have a look at our schematic. On the far left, we have our battery, the 3.7 volts, going to a Phoenix connector that's going to be on our board. And then this circuit is a recommended design from the data sheet. That's how we came up with these capacitance values and inductance values. And then it outputs the 3.0 volts and the 3.3 volts. Next, we have our microcontroller, and we have our decoupling capacitors connected to our power pin on there, as well as you can see the sharing of the pins that I pointed out earlier, as well as the load switch enable and the accelerometer interrupt. And then this is a no shutdown pin for our CC1310, so we can conserve power by turning that on and off, as well as the JTAG down here. Then we have the CC1310 simple link, which has all the decoupling capacitors going to all our power pins, as well as our oscillator connected to the 2 pins for that. The no shutdown pin, which is pulled high, as well as over here, this is the balun for impedance matching, which then goes into that 100 picofarad capacitor and then to an antenna connector. Here are our temperature sensors, where we show our 1 kilo ohm pull-up resistors for I2C, as well as over here, this is the weak zone bridge circuitry. And this capacitor up here, I'm going to give you more detail about that when we look at the layout. That is used to give a more accurate reading. It goes on the back side of the board, so it's more, so whenever it's measuring across the ADCs, it gives a more accurate measurement. And that is connected to the load switch, which is powered by the 3.0 volts. The last component of our schematic is the accelerometer, which has the chip select, which is used, which has a 10 kilo ohm resistor, which is used to put it in I2C protocol. mode, as well as we have the accelerometer interrupt, which is going to the MSP430. And now we'll take a look at the layout. This is a 2-inch by 2-inch layout. Using most components are the resistors and capacitors are 0603, unless otherwise stated. C5 is actually a polarized capacitor, which is a 3216 footprint. As well as if you look up here, U1, where all this is, that is the exact way where you have to, because the voltage regulator has to be, cannot use traces for it to properly work on your board, so we had to match that exactly in the layout. And then U2 is our MSP430. This is our 1310, which goes through the bound, which is quite small, which needs these ground pads around it, so it stays, so it matches the impedance properly. Then it goes into a 50 ohm trace, which is 17 mils, over to our antenna. We have two different power planes. This section right here is 3.0 volts. The rest of it is 3.3, and then there's no power plane below the antenna. And that is it for the layout. Oh, and then what I pointed out earlier was that capacitor for the weak zone bridge is going on the back side. So the red is on our very top layer, it's a 4-layer board, and the blue traces are on our bottom layer. And so we have these two ground rails, which are used to also make sure we get an accurate reading across that weak zone bridge. And next we have our enclosure. This is our enclosure where our board is actually going to go inside. It's going to go inside this area. It's modeled after a typical cow ear tag. And the hole up top here is where our RTD temperature sensor is going to go out, and then the lead is going to go to the cow to measure that temperature, make sure we're getting the cow's temperature. And then the other enclosure we have is on a receiver side, where we're going to have the CC1310 development board inside here, with the hole right there is where our antenna will go out, and then it'll be screwed on there, and that will be on the server side where we can receive all the data that our other 1310 is sending packets to. Next we have our flowcharts.
Okay, so let me going over our software flowcharts for MSP430. First up, we have our main, where we need to disable our watchdog timer and also disable our GPIO high impedance mode. Next, we're going to be calling all of our configure functions, including our real-time clock, ADC, our UART, our pin int, which is our interrupt coming from our accelerometer, our I2C communication, our accelerometer itself, and our control pins going out to power our simple link and our Wheatstone bridge. So first up is configuring our real-time clock. We're going to be using our A clock, which is at 32 kilohertz. It's necessary to run it so low so that it'll work in our low power mode. Next, we're going to be dividing that clock and setting a compare value so that we can interrupt every 1 second. Next, we need to enable the interrupt for that clock, and then we return. For our configure ADC, we're going to be configuring our ADC 0 and ADC 1. Those are pin 1.1 and 1.0. We're going to be sampling those pins over a 16 clock cycle, and they're both 10-bit. We're also going to be using single sample mode, which means we'll only be taking one sample every time we call for a measurement. We're going to be using an ADC reference voltage of 1.5 volts. We need to enable our conversion complete interrupt that allows us to convert the information we're playing off of something usable. The last step is to unlock our PMM registers so that we can enable the internal reference, which is just our reference voltage to 1.5. We're going to also delay to give that reference time to settle. Next, we're configuring UART. UART is going to be pin 1.6 and 1.7 for us. First thing we're going to do is set up those pins for UART mode. USCI is our communication interface that comes with our MSP430. We put that into reset so that we can configure it into UART. First, we're setting the SM clock as our source, and we're going to be using UART 3 significant bit first, 8-bit data link, and 1 stop bit. We're using a standard 9600 baud rate. Then we need to reinitialize our USCI and enable the RX interrupt. For our configure pin int, and again, that's the int coming in, or the interrupt coming in from our accelerometer into our MSP430, so we know when it's ready to take that off of. We configure the pin for an interrupt. We also need to enable our pull-up resistor. It's going to be active high, enable the interrupt. And we're also going to clear the flag off right in the configure to make sure it's ready to go whenever we get that first interrupt. For configuring our I2C, First, we have to set up our pin 1.2 and 1.3 to use I2C mode. The communication interface here, the USCI, is the B version. It's just the same as the others, just for I2C. We put that in a reset so we can configure it. We're going to be putting it into synchronous I2C master mode. So our MSP430 is our master for our I2C communications. The bit address is actually 7 bits instead of 8. We use the last bit for read or write. We're going to be using that at a frequency of 100 Hertz, which works with both our accelerometer and our digital temperature sensor. Then we need to set our slave address into the proper register, take out a reset, and enable our interrupts. The next thing we need to do is configure our actual accelerometer, and we're doing that over I2C. So the first thing we need to check is to make sure that the I2C bus is ready to go and can send data off to the accelerometer. Then we set our start condition, which puts our start condition on the I2C line, and also triggers our TX interrupt in the I2C interrupt service routine. Once it goes into that TX interrupt, it's going to go through an array of hex values, which are going to configure the registers in our accelerometer to the settings we want. We also need to enter low power mode 0 so that I2C will be able to run. Okay, for configuring our control pins, and these are the pins we're going to be using for turning our simple link on and off through the no shutdown pin, and also powering our Wheatstone bridge through a load switch. We just need to clear, the setup is really simple. We just clear the port 2 latch so that we can set the output direction to the direction to output, and then we also set the pins low for starting output so those aren't powered whenever we first turn the device on and start running it. For the interrupt vector for port 2, this is again the interrupt coming in from the accelerometer. We're going to disable interrupt so it doesn't get interrupted by something else, and then request data from the accelerometer and take that data and store it to the FRAM. The FRAM is permanent memory or non-volatile. Now every 3 hours we're going to be taking a temperature measurement on our digital temperature sensor through I2C. So every 3 hours this function is going to be called, and it's going to start off by sending a request to the slave for the data. It's going to delay for about 0.1 seconds, and then it's going to see if that data came in through the RF interrupt. And if it has come in, we move on. If it has not, it tries again 3 times until it times out, stores an error code, and returns. So once that data does come in, it's going to read the data out of the buffer, validate that the data is good. If it's not good, we're going to store a different error code and return. If it is good, we're going to store that to data one store and move on to taking a second measurement. And we're going to do that for a total of 3 times, taking 3 measurements from our temperature sensor. So once we've got our 3rd measurement and we know that it's good data, we're going to average that data out to one value and save that to our FRAM. Here's our I2C interrupt service routine. This is what's going to be controlling those communications that we were just talking about. Right away, we disable interrupts to prevent it from getting interrupted in the middle, and go into a switch case. Just to cover this real quick, and somehow if it gets in here and there's no flag, it just re-enables and breaks out. If the TX interrupt is flagged, meaning that we've initiated I2C communications, it checks to see that the data ready flag is there. That means we have data that's actually trying to go into the TX buffer. If there's not, then we simply send the stop condition, the stop I2C, disable the interrupts, reset, and break. But if it has, then we do the exact same process, but we load the data out of the buffer and store it first. Over here on the RX side, as soon as that RX interrupt goes off, we're going to read the data out of the buffer and then validate that data, making sure it's what we're looking for. If it's not, then we just reset and break out. If it is good, then we're going to store that data, reset, break out. For our ADC temperature measurement, that's our analog temperature measurement that's going to be coming off the cow. When we call that once every 3 hours, along with the other temperature measurement, we need to first enable the load switch so that we power our Wheatstone bridge. After that, we read in the data from our ADC 0 and ADC 1 and validate that data. If the data is bad, store an error code, return. If it's good though, we compute the difference in the 2 values, store it, and then do that 2 more times for a total of 3 measurements. Once we have our 3 measurements, we're going to average it out. We're going to be storing that value And then we're going to disable the load switch again so that the reselling bridge is unpowered. And then returning.
All right, so here we have our RTC interrupts. This is the RTC interrupt vector, and when the RTC interrupt goes off every second, it sets the RTC flag and sets the increments the RTC second variable counter, and it then checks to see if this has gone up to 60 or not. If it hasn't, then it's going to clear that flag, break out, and then it'll be interrupted again, and it will check again. So if it has, we're going to increment the RTC minute variable counter and set back the RTC back to 0. And we're going to do this for minutes as well as hours, and we're going to be going up to 3 hours. So if we are below the 3 hour mark, we're going to clear that again and then keep going until we finally are. When it hits that 3 hour mark, we're going to go into our measure, compile, and send function. So here is where we're going to be calling our measurements for our I2C temperature sensor as well as our ADC temperature. And we're going to be compiling that data into a packet and then transmitting that. So this data compiler function checks to see if we have a temperature value that we need to be sending. If there is, then we're going to be reading in the temperature measurement from memory and then reading in the rest of that packet accelerometer data. And then we're going to concatenate this data into a packet, compute the CRC using our built-in 16-bit CRC and adding that to the end of the packet. If there is no temperature data, then we're going to be filling the next packets up with accelerometer data. And that is going to be filled into packets and added as CRC as well. So our data transmit function is going to be sending our packet from the MSP430 to the CC13 pin. And first of all, we have to turn on the simple link with the no shutdown pin on the MSP430. So we're going to be checking for previously stored data, because if we, for some reason, can't connect to the, or don't get any response back from the receiver, we want to save that data in FRAM and then send at the next time interval. So if the data is not in memory previously, we're going to be writing out that current packet to the CC1310. If there is a previously stored packet, then we're going to be going through a timeout. So if we get an acknowledgement, if we don't get acknowledgement, we're going through in a timeout. It's going to check 3 times to see if we're going to get an acknowledgement or not. And if we do, then we move on to write the next packet. If we don't, it's going to discard that data and store current data in. And then turn off the simple link and return an error code. So we're going to send that current packet and do the same sort of error checking. And then if we can successfully send that packet, we're going to turn off the simple link and return that function. So here is our interrupt service routine. First of all, when we go into this, we're going to disable interrupts, and then we have a switch case for TX as well as RX, as well as a no interrupt flag. Just in case it gets in that no interrupt flag for some reason, we're going to enable interrupts and break out of that. If it goes into the TX interrupt flag, we're also going to be enabling interrupts again and breaking out of that. And if it gets RX, that's for our CRC checking, and we're going to be reading from the RX buffer and storing that data and resetting the interrupt flag and then enabling and breaking out of this. So here is for the CC1310 side software. So we're going to be operating in a real-time operating system, and this is for our URN and our RF out. So for our main, we're going to be initializing our general board initializations, as well as getting in handles and calling our task init function, and then starting those with the BIOS start. In the task init, we set the handles, create a new task param pointer, and initialize the parameters for this pointer, and then construct the task. In the task function, we initialize our variables and arrays, our GPIO and UART, and then set the handles, and then we initialize our RF and our UART parameters. Then we open our UART so we can read UART in, and then close it once we're done. And we're going to open our RF, and we're going to set the frequency and then send over that frequency. So on the receiving CC1310, we're basically going to be doing the same thing, but we're going to have RF in and UART out. So we're going to be doing the sort of same board initializations, GPIO and UART. We're going to get the handle and call that task init function again, and then start those with our BIOS start. In the task init function, we set the handle, create new task param pointers, initialize the parameters for this pointer, and construct the task. So in this task function, we're going to be initializing the RF parameters, opening up RF, setting to the frequency, and reading in. And we're going to be reading in continuously. So when we receive over RF, we're going into this callback function, and here we initialize our array variables and arrays, and we call this RFQ to get our data, and we initialize our UART, open UART, and write that data out to UART to our serial interface on our computer. So here is our database listener, which is a Java script that we will have on the computer that will be listening to our serial line, and that's going to check to see if UART connection is available. We're going to try to connect 3 times. If not, we're going to return an error code. Then we're going to be setting up a database connection. If we can, then we move on. If not, we're going to try again 3 times. If we can't connect, then we're going to return an error code. So once we're connected to the database, we're going to begin to listen to UART. And we're going to be checking for packets received and checking to see if the data is valid. If it's not, we're going to be discarding this data and continuing to listen to UART. And if it is valid, then we'll store in the database, and it is looped, and it'll go on for as long as we have the program running. So here we have our database listener. So this is to set up a connection between our Java program and our database. So here we set up a connection to the database and go through that same error checking here. And then we're going to retrieve from the database and display that on a web page.
Our demonstration here. This first demonstration is just a bench test, just to show it all working together as a unit. We will be listening narration of what's going on. This is the nPhase prototype progress demo. This is the setup we'll be using.
In this demo, we'll be using an MSP430 launchpad to take a voltage difference across an RTD sensor through a Wheatstone bridge. We'll be taking this data as an hexadecimal format through UART to assembly. On the final web page, you'll see this as a value between 230 and 250.
The CC1310 Launchpad will be receiving a packet from the MSP 430 via UART. It's going to then take this packet and send it over RF to the other 1310 module. Once this packet is sent, a green LED will blink here. Once this is received, a red LED will blink.
Once the packet is received on the 1310 on the side, it will then transmit it via UART to the USB COM port on the computer. On the computer itself, there is a program listening to the COM port that will take any data received and store it into a database. The database is then pulled by a web page, and it will update and display in this table. As you can see, if we refresh the web page, there's no data at the moment. We will begin by starting the COM port listener. It started. Next, we start the RF listener. The CC1310 is now waiting to receive.
We're now going to begin sampling voltages and transferring the data over UART.
As you can see, the light is green here, that means it's sent. Come over here, the light here is red, that means it's received. If we go back to our web page and refresh, the data is there, value of 232. Second demonstration, it's our distance demonstration, and it shows that we are able to meet the functional requirement of distance, being able to transmit over 50 meters. This particular demonstration was done at around 60 meters. So here's our web page. If we refresh here, you can see there's nothing here. We're going to start the database listener. It's now started. Then we're going to start our RF listener. That's now started. When we receive a packet, this LED here will turn red.
Ready to receive, guys, whenever you're ready.
Alrighty, we are sending.
Now.
See, we received, and if we refresh the page here, there's our data. So now for our summary of our project, our overall status, our completion date is scheduled to be on the 13th of December. Currently, we are under budget. Our labor hours are 686.5 hours out of 1,454 budgeted hours. Materials cost so far is $1,054.69, a budget of $2,915. Our accomplishments so far, we have RF transmission and receive communication between our launch pads, UART communication between our MSP430 microcontroller and our SimpleLink launchpad microcontroller, communication of data from our RTD sensor through the ADCs all the way to our whole chain to the web page, which we just demonstrated. And we also just recently ordered our alpha board that should be in by the end of the week. Missed goals, we are still working on alpha source code. We major tasks completed. We've got our software flowchart design, alpha schematic, alpha layout has been approved, and the alpha board has been ordered. Major tasks remaining include alpha source code completion, CDR approval, hopefully today, beta board order, final code completion, final demonstration, and our sign-off. Our schedule, see here, the alpha schematic and alpha board have completed. Again, we're behind on alpha code completion. We've got CDR approvals today. Beta board, we're hoping to have done early November, ordered early November. Hoping to complete our source code by mid-November, November 17th. Our final demonstration is November 28th, and then our sign-off is the 8th. Our current predictions, alpha source code, we're predicting to be done by the 18th of this month. Beta board, again, hoping to be ordered by the 15th. Our source code, final source code is hopefully completed by the 22nd. Final demonstration is scheduled for the 28th, and sign-off is the 8th. is our high-level Gantt chart that shows how we're doing. Green means that we are ahead of schedule, red means we're behind schedule. If we go into our low level, this is what's upcoming in the next month or so. We've got our alpha layout design is done. We'll hopefully begin layout design, beta layout design, which we've got alpha layout and we've tested. We're behind in software, as we mentioned earlier. We're hoping to have that done by the 17th to 18th. Let's see. We've already ordered our alpha PCB and the parts, so we're just waiting for the PCB to come in, and we'll begin populating that. And documentation is a bit behind because it was pushed back by the software. The software is part of the critical path. For financial status, total number of hours for the teamwork this week is 166.5 hours. Total hours for the semester is 790 hours, 790.5 hours. Average hours per week is 131.75 hours. Total baseline hours that we estimated last semester was 1,454 hours. Estimated hours to complete, this is the hours we have left, is 665, which comes out to about 95 a week. Budget status, we're an hour and a half of the budget, which comes out to be about $52.50 for the budget. For materials, the baseline estimated expenditures was $2,915. Our expenditures this week were $331.40. Expenditures to date is $1,054.69. The estimated remaining expenditures is $1,200, and that means we are $660.31 under budget. So in conclusion, we spoke about our problem statement, our concept of operation, went over our project, gave a technical presentation, demonstrated our project, and gave a summary of how what our progress is so far. Any questions?
So do you have any idea of how you're going to put that temperature probe in the cow's ear and how it would stay there?
There is some, we've spoken with the owner of the company, Awesome, and he mentioned they have some sort of, it's like a biodegradable tape or something, I think is what they call it. It's an adhesive you can stick on there, and whenever they would change the battery every month, they would have to reapply that.
Could you go to slide 59, please? Your current team hours per week on average is 131, and your estimated hours to complete is 95 per week. Are you all worried about that at all?
We're pretty regularly meeting. Our average is kind of brought down because when we first started, we weren't working this much, but we're working, I would say, more than 135 a week, or at 135 a week on average now. So I don't think it's much.
Cool.
Yes, sir.
Can you share with us how you computed your estimated hours to complete?
We actually have a Excel sheet that I created with all of our tasks, and every week I have every member who's the leader in that task go through and give us how much time they think that task is going to complete as of now. And at the very end, it totals that all up for us and gives us our hours estimated.
And you're really that close to your baseline?
At the moment, yes.
You mentioned a number of times about generating an error code. I don't recall hearing any information about what you're going to do with those. Where do they end up at? What are they used for?
They're going to be transmitted to the server so that it'll pop up right in the database so that you'll see that there's something wrong with that tag, and the error code will correspond to what's wrong.
Okay, I missed that.
Any further questions?
Show the picture of the housing you're going to put the tag in. How heavy is it going to be once everything's in? How does it compare to a typical plastic tag?
We haven't actually compared that. That is something that we'll look into. The components are so small on the board shouldn't be very heavy at all. And then,
The battery too?
right.
The The battery's probably gonna be the biggest amount, but even then, it's not all that big. And then the PLA plastic is pretty lightweight.
Based off experience, it should be only slightly more than a normal compared to
So for your power, if you want to go back to the conceptual block diagram, is that the battery that y'all are going to be using?
Yeah, so the battery we have is 3.7 volts, and it's regulated down to 3.3 for that microcontroller. Then we have 2.0 going to the Wheatstone Bridge, the one that goes to the cascade.
And so
That is the actual.
That's the actual battery.
that is the actual battery?
Yes.
And so there's no charge circuitry, so this is going to be a battery that's replaced? And,
Yeah, that would be something they would unplug and they would charge.
and it's not meant to be, are you going to, is the consumer or is your sponsor expected to recharge this battery and then be able to replace other ones?
Yes, they should, it's just a Phoenix connector, so they can just unplug it, charge it however they need, and plug it back in.
And the capacity of the battery?
It's 850 milliamp hours. And I have a whole power budget that I've been making, and it's everything in data sheet divided by, we actually have a little bit over a month. So that meets our requirement for power.
For y'all's packaging, these are going to go on the actual cows, right? Like the ear tag? Have y'all taken into consideration that this is going to be outside, it's going to get rained on, it's going to be, cows are going to scratch it? Have y'all taken the durability of it?
These, for our sponsor said that for these prototypes, they will be only using them in a barn. So they will not actually be outside. And as they're going to be swapped, or you can go in and replace the battery every month, so if there's anything to clean up, they can do it at that point. That's something, that's a risk we're passing on to our sponsor.
How far away is the temperature sensor in the cow's ear from your board? Like, is it connected through a cable? Have you tested, like, if the signal, like, is messed up anywhere?
There is actually specific cabling for our TV sensors. It's a twisted pair with some special shielding on it that is made to deal with those kinds of issues.
In the near future, are these meant to last like a very long time, or are they more meant to be like somewhat easily replaceable if they are damaged?
somewhere in between, probably.
Yeah, probably a little bit in between.
With the 1 hour battery life, we assume it should at least last that month.
Right.
So you're going to make 3 observations per measurement in most cases.
Yes.
Why did you choose 3, and have you actually looked at the data to see how much variation you get in 3 consecutive measurements?
That was originally the reason we chose 3, was to make sure if for some reason we got some outlier value, we wouldn't be completely thrown off by it. We have
Why not use 10?
3 was just, that was what was, it was enough to average something, but it wasn't too much that we weren't, overusing it and draining our battery, taking more measurements than necessary.
But you haven't
We
evaluated.
haven't tested that yet. We can do that. Yeah, that was something we can look into.
Any other questions?
One more question. For you, in your demo, you showed us the antenna being able to communicate with the other one. That was on a development board, correct? So my question is, do you have an antenna that you're designing and placing on this, or is it a module that's already designed for
So
it?
if you go to the CBD, it's actually, on the CBD, it's actually what we're planning to do with, on the breakout board, there's a capacitor we can, so you can't really see it, but right over here, there's a capacitor we can remove. So then, because this is the antenna on the breakout board, and if we remove the capacitor, we can then use this to attach an external antenna. And so this is adapted for that, and we're attaching that.
And on the module itself, it's going to have a stick antenna that's going to stick to the top of the enclosure.
And you're not designing that, that's something.
No, it's
That's
just
what we're
an
purchasing.
option.
Thank you very much, and thank you.